Your time starts.
In the last lecture, we had started deriving the conservation equations in a general orthogonal coordinate system. Orthogonal is a coordinate system where the three coordinate directions are perpendicular to each other at all locations in space. The coordinate axes do not in general, planes perpendicular to the coordinate axis do not in general have to be flat surfaces. In the cylindrical or the spherical coordinate system, we saw that the surfaces of constant r are either cylinders or spherical surfaces. However, at each location in that coordinate system, all the three surfaces were perpendicular to each other. So, this analysis is restricted to coordinate systems where all three surfaces are perpendicular to each other. The first coordinate system that we had chosen was a Cartesian coordinate system. In this coordinate system, the axes are x, y and z, and the surfaces of constant coordinate are planes perpendicular to the x, y and z axis. There are three unit vectors along the coordinate directions Ex, Ey and Ez. All of these are perpendicular to each other and they have unit length, okay, as expected for a orthogonal coordinate system. Important point to note about the Cartesian coordinate system is that the unit vectors are directed, the direction of the unit vectors is the same at all points in space. That is, the direction of the unit vector does not change as you change location. Okay, so, it is the same at all coordinate points in space. We had taken a cubical volume of side delta x, delta y and delta z, which was bounded by 6 surfaces, 2 perpendicular to the x axis, the front and the rear surfaces, 2 perpendicular to the y axis, the left and the right surfaces, and 2 perpendicular to the z axis, the top and the bottom surfaces. And the unit vectors at each of these surfaces are shown in the figure here on the right. And so, you had 2 surfaces which are the rear and front surfaces perpendicular to the x axis, 2 surfaces which are the left and the right perpendicular to the y axis, and 2 surfaces, the bottom and top perpendicular to the z axis. Their surface areas are the products of the 2 increments perpendicular to the coordinate. So, for the surface which is perpendicular to the Ex coordinate or perpendicular to the x axis, the area is delta y times delta z. For the left and the right surfaces perpendicular to the y axis, the area is delta x delta z, and the bottom and top surfaces perpendicular to the z axis, the area is delta x times delta y. And the equation was what we had used earlier in a one dimensional coordinate system, okay, except that this is now being written for 3 dimensions. Change in mass in time delta t is equal to mass in minus mass out plus production of mass in differential volume. We had expanded out each of these terms. Okay, the change in mass is the change in concentration times the volume, okay, whereas the mass in at the surfaces on the rear, the left and the bottom is the product of the flux in that direction times the surface area times time. Okay. The flux times the surface area times time. The flux itself contains the product of the sum of the diffusive and the convective fluxes. Convective flux is the concentration times Vx, and the diffusive flux is just Jx, okay, the flux in the x direction. So, we can write down the masses in and masses out at the 6 surfaces, okay, and the rate of production, substitute that into the balance equation and divide by volume delta x, delta y delta z and time delta t. Okay. So, you divide throughout by volume and time to get a difference equation, and then take the limit delta x, delta y, delta z going to 0 to get the differential equation. Okay. So, that was the procedure that we had followed. And the differential equation was written here. Okay. So, the differential equation in terms of the fluxes, okay, the differential equation in terms of the fluxes contained the convective terms on the left and the diffusive terms on the right. The diffusive terms were the derivatives of the components of the flux. Okay. The components of the flux are related to the gradients in the concentration in the respective directions. So, the components of the flux are minus d times the gradient of the concentration in that particular direction, gradient being the partial derivative, okay, in the respective direction, where d is the diffusion coefficient. The negative sign because the transport of mass takes place from higher concentration to lower concentration. Therefore, the flux is positive if partial C by partial Z is negative. Okay. So, Jz is positive if partial C by partial Z is negative, and so on. Okay. And based upon this, we had got different expressions for the mass conservation equation. This one applies for the general case where fixed law of diffusion applies, but the diffusion coefficient is a function of position. If the diffusion coefficient is independent of position, then the diffusion coefficient can be taken out of the derivative, and this is the result that we get. Okay. So, this is the mass conservation equation. Now, if you recall, I had this particular expression for the flux. Okay. The flux is a vector. What I have written here are its components. The flux is in general a vector. Vector j is equal to jx ex plus jy ey plus jz ez in a Cartesian coordinate system. Okay. Similarly, the vector v is equal to vx ex plus vy ey plus vz ez, okay, in a Cartesian coordinate system. Here I will use underlines for vectors. Usually the bold face is used when printed text to denote a vector. Okay. And Ex, Ey and Ez are the unit vectors. Okay. If I substitute the constitutive relation into the expression for the flux, this becomes equal to minus d into Ex partial C by partial x plus Ey partial C by partial y plus Ez partial C by partial z. Okay. That is the expression for the flux, okay, if I substitute the Fick's law for diffusion. Okay. And this I can write in terms of a vector operator, okay, the gradient operator as minus d times the grad of C, okay, where this gradient is a vector. Okay, it's a vector which is defined. It's an operator which acts on a field variable, okay, which acts on a function of position, and it is defined as grad of something is equal to Ex times partial by partial x plus Ey times partial by partial y plus Ez times partial by partial z. Okay. So, this is the gradient of the concentration field. Okay. And so, for example, if I write the gradient of the concentration field, this would be Ex partial C by partial x plus Ey partial C by partial y. So, now this relationship, this constitutive relationship J is equal to minus d times the gradient of the concentration. that is the relation between two vectors. Okay. It is independent of the coordinate system. Okay. It is independent of the coordinate system that is used. Okay. So, for example, if I had an x, y, z coordinate system, okay, okay, at some point the vector grad c, okay, this is the vector grad c, okay, the gradient of the concentration. This is a vector in space. Okay. As we will see a little later, it is directed along the direction of maximum variation of concentration. Okay. So, this is a vector in space, okay, and it has components. Okay. The components of this vector are, okay, E x partial c by partial x plus E y partial c by partial y plus E z partial c by partial z. Okay. These are the these are the components of the concentration variation. Okay. If I were to change my coordinate system to some other coordinate system, okay, let us say that I would to change my coordinate system to something else, okay, x, y, and z primes, okay, x prime, y prime, z prime. Okay. Rotate this coordinate system, say, by some angle, okay, in 3-dimensional space. Then this would be E x prime, okay, partial c by partial x prime plus E y prime partial c by partial y prime plus E z prime partial c by partial z prime. Okay. Now, the 3 unit vectors are different. Okay. They are not the same as the unit vectors x, Ex, Ey and Ez that I had earlier, okay, because now I have a rotated coordinate system. The components are also different. Okay. The derivative with respect to x prime, y prime and z prime are in general different from the derivatives with respect to x, y and z. Okay. So, they are in general different. So, the components of the flux depend upon the coordinate system that is used. I am sorry, the components of the velocity gradient depend upon the coordinate system that is used. However, the gradient itself is a vector in 3-dimensional space which has a specific magnitude and direction. That does not change when you change the coordinate system. The flux is a real quantity in space. The coordinate axes are chosen by the observer in order to analyze the flux. So, the choice of the coordinate system does not change the flux. Okay. And similarly, the choice of the coordinate system does not change the gradient also. Okay. So, it does the gradient vector is a vector that is directed in one particular location in space at a point. Okay. So, the choice of the gradient the coordinate system does not alter the value of the vector gradient of the concentration, though the components will change, because the gradient of the concentration is something physical. Okay. It is the difference in concentration between nearby locations, okay, divided by the distance travelled. Okay. So, that is not going to change. Okay. So, this relationship is a relationship between two vectors, okay, the constitutive relation here is a relation between two vectors that is independent of the choice of coordinates. When you want to determine the components, of course, you have to assign a coordinate system and determine the components in that coordinate system. However, the vector itself has an identity, a magnitude and a direction that is independent of the coordinate system. Okay. The other thing to note, the gradient operator here acts on a scalar. It acts on a scalar function and the result is a vector. Okay. The gradient operator, it acts on a scalar and the result is a vector. Okay. So, that is the constitutive relation. Okay. If you recall, the conservation equation was partial c by partial t plus partial by partial x of c v x plus partial by partial y of c v y. plus source term. Now, this summation over here, okay, this summation over here, okay, partial j x by partial x plus partial j y by partial y plus partial j z by partial z. Okay. I can alternatively write this as the dot product of two vectors, okay, E x partial by partial x plus E y dotted with j x E x plus j y E y plus j z. This is an alternative way of writing the expression, where the dot there is the dot product between the unit vectors. Okay. And recall that the dot product E x dot E x is 1, E y dot E y is 1, and E z dot E z is 1, whereas E x dot E y etc. are all 0. If the two unit vectors are not the same, then the dot product is 0. And if you use that, you will get the same expression that I have on the left. Okay. And this can be written as del dot j, okay, where this gradient is this gradient operator. Okay. It's the same as this gradient operator. It acts on a vector, okay, and results in a scalar. Okay. You can see that the term on the left here has no unit vectors. Okay. So, it is just a scalar. Okay. So, this is called the divergence. Okay, of the vector j. The divergence of a vector is a scalar. Okay. So, in vector notation I can write this entire equation. Okay. In vector notation I can write this entire equation as partial c by partial t plus the divergence of the velocity times c on the left side. Okay. You can see that you have here partial by partial x of c v x, partial by partial y of c v y, and partial by partial z of c times v z. Okay. That is just divergence of the vector v times c. Okay. On the right hand side I have is equal to minus of the divergence of j, vector j, okay, plus the source term. Okay, where recall that the vector c and the vector j are given by this. Okay, the component times the unit vector. Okay. So, therefore, this is the equation, mass conservation equation written in vector form. Okay. As I said, the individual components of the gradient do depend upon coordinate system. Individual components of the velocity and the flux do depend on coordinate system. However, the gradient of the concentration, the divergence of the velocity and the flux, they do not depend upon the coordinate system. Okay. Since the result is a scalar, that result has to be the same independent of coordinate system. Okay. If it were not true, then you could change a physical quantity, okay, the divergence of the flux, just by rotating a coordinate system which you have created. Okay. So, that is inconsistent, and therefore, these have to be independent of the coordinate system that is used. Okay. And finally, in the second term I substitute the vector flux is equal to minus d times the divergence of c. I am sorry, this is not the divergence, this is the gradient of the concentration. Okay. Divergence acts on a vector, the gradient acts on a scalar. Okay. So, substituting these into the conservation equation, I get partial c by partial t plus the divergence of V times the concentration is equal to minus the divergence of minus d gradient of C plus the source term. And of course, this minus and minus will give me a plus. Okay. And if the diffusion coefficient is a constant, okay, this is the general expression. If the diffusion coefficient is a constant, I will get d times the del divergence dotted with the gradient of C, okay, the gradient operator dotted with itself. Okay. So, what is this? Okay. Okay. This is equal to E x partial by partial x plus E y dotted with itself dot product of two unit vectors is 1 if they are the same and 0 if they are different. So, this is just equal to partial square by partial x square plus partial square by which is often written as del square. Okay. Del square is an operator, it is called the Laplacian. Okay, the Laplacian operator. Okay. And the conservation equation is written as partial C by partial T plus you recall that this operator is the same that we had earlier in our conservation equation, that is this one here. Okay. This is the operator that we had. The sum of the second derivatives with respect to x, y and z. Okay. So, that is the Laplacian of the concentration field. Okay. So, this is the conservation equation in vector notation. Okay. This is the conservation equation using vector differential operators. This conservation equation is the same regardless of what coordinate system is being used. Okay. I just told you that the vector flux and the vector velocity do not change if you rotate a coordinate system. The components change, but the vectors themselves are physical entities that do not change direction or magnitude if you rotate the coordinate system used for observation. Okay. Similarly, the divergence of quantities cannot change if you change the coordinate system. Similarly, as we shall see a little later, even if we switch from a Cartesian to a cylindrical to a spherical coordinate system, the equation written in vector form is exactly the same. Okay. The meaning of these vector operators, the gradient, divergence and the Laplacian, those change when you go from one coordinate system to the other, but the conservation equation in terms of the vector differential operators is unchanged. Let us look at the left side of this equation, okay, partial C by partial T plus okay, I can use product rule for differentiation to differentiate these products of the velocity and the concentration. Okay. So, this is equal to partial C by partial T plus V x partial C by partial x okay, using the product rule for differentiation. Okay. And you can easily verify that this combination can be written in vector notation as V vector dotted with grad c plus c times the divergence of the velocity. Okay. Okay, so that I can write the conservation equation as partial c by partial t plus v dot grad c plus s. So, what do these terms mean? Okay, what do these terms mean? So, let us take a concentration and velocity field in 3 dimensions. Okay. You have some flow field and some variation in concentration, okay, in this 3-dimensional space. Okay. And if you have some volume element of fluid, okay, occupying some location at the, this is the location x and t. Okay. X vector is x e x plus y e y plus z e z. Okay. On this is superposed a velocity. Therefore, this volume element at a later time will occupy some other position. Okay. If you take a volume element that is moving along with the fluid, at a later time this volume element will occupy some other location x plus delta x, t plus delta t. Okay. It will occupy a new location x plus delta x and t plus delta t, okay, where delta x is equal to V x delta t. The displacement in the x direction within a time delta t, delta y is equal to V y delta t and delta z is equal to V z delta t. Okay. So, I am not considering a differential volume that is fixed in space, but rather a differential volume that is moving with the same velocity as the fluid velocity at that location. Okay. Therefore, the displacement made by this differential volume, this material volume element will be delta x, delta y, V x delta t, V y delta t and V z delta t. Okay. The derivative moving in this reference frame, okay, the derivative of a quantity moving in this reference frame is what is called the material derivative or substantial derivative. Okay. The derivative in a reference frame moving with the same velocity as the fluid velocity at that location. Okay. That is the concentration at x plus V x delta t, y plus V y delta t, z plus V z delta t. Okay. Minus c of x, y, z, t. Okay. The difference in the concentration at the location x plus V x delta t, y plus V y delta t, z plus V z delta t and t plus delta t at the time t plus delta t. Okay. At this new location at the time t plus delta t minus the concentration at the old location at time t, okay, divided by delta t is what is called the substantial derivative written with a capital D. Okay. This is the substantial derivative written with a capital D. Okay. And you can do the differentiation by chain rule, and what you will get is that dc by dt is equal to partial c by partial t plus Vx partial c by partial x plus Vy partial c by partial y plus Vz partial c by partial z, okay, using chain rule for differentiation. Okay. So, that is the substantial derivative, and this is also equal to partial c by partial t plus, if I express it in vector notation, v dot grad c. Okay. V dot grad c is Vx partial c by partial x plus Vy partial c by partial y plus Vz partial c by partial z, that is V dot grad c. Therefore, this combination, the first two terms here, is the substantial derivative, okay, dc by dt. Okay. When expressed in terms of the substantial derivative, this is dc by dt plus c divergence of v, okay, is equal to d del square c plus s. Okay. Okay, so, this is how the derivative can be the convective term can be equivalently expressed in terms of the substantial derivative, which is the derivative, the difference in the concentration divided by delta t of at the location x plus v delta t at time t plus delta t and x t at the time t, okay, in the location x at the time t. So, take the difference between the concentration at the location x plus v delta t, the location to which the volume moves at the time t plus delta t, minus the concentration at the original location x at time t and divide by delta t. Okay. And this is the definition of the substantial derivative.